Hello students and welcome to Chemistry B. I'm Miss Slate and today we're going to be talking about gas stoichiometry. So basically how the ideal gas law and stoichiometry can come together when we are given, volume of a gas that's not at standard temperature and pressure. So our first example here simply says, what is the volume of carbon dioxide at STP that is produced from 995 grams of iron 3 oxide? And they give us the balanced chemical equation for the reaction below. Now, if we look at our stoichiometry roadmap, we are starting with mass of the iron 3 oxide. We're going to need to go to moles of iron 3 oxide, which we can then go to moles of carbon dioxide. And then because they told us the gas was at STP, we can simply then go from moles of carbon dioxide to volume. So we'll start it like we would just run this like we would a normal stoichiometry problem. And so we get a final answer of, rounding to sig figs, 401 cubic decimeters of carbon dioxide produced in this reaction. So when a gas is at standard temperature and pressure, we can do these problems like normal stoichiometry. The new part that we're going to learn today is what happens if they're not at standard temperature and pressure. So, for example, this says 5 liters of nitrogen reacts completely with sufficient hydrogen at a constant pressure and temperature of 3 atmospheres and 298 Kelvin. How many grams of ammonia are produced? Well, if we were to look at our Stoich roadmap, we would want to go from volume straight to moles, but we're not at standard temperature and pressure. Right, we are at 3 atmospheres and 298 Kelvin. Standard temperature and pressure is 1 atmosphere and 273 Kelvin. So we have to do a little bit of a detour, okay? So before we're able to go from volume to moles of our starting nitrogen, we're gonna have to use the ideal gas law to determine that. So we'll take the pressure, volume, and temperature given to us and use the ideal gas law to determine the moles of nitrogen. From there, once we have the moles of nitrogen, then we can convert to moles of ammonia. So like I said, the first thing we need to figure out is moles of nitrogen. So again, the ideal gas law, PV equals nRT. Solving it for moles is going to make it pressure times volume divided by the gas law constant times temperature. And again, this is specifically for nitrogen, our reactant that we're starting with. So then I would just put my given information into the ideal gas law. And when we do the math for the ideal gas law, we end up with 0.613 moles of nitrogen gas. Now that we've used the ideal gas law to determine moles of nitrogen at a non-standard temperature and pressure, to get to grams of ammonia, we can now pick up with normal stoichiometry. So at this point, I would take my 0.613 moles of nitrogen, convert it to moles of ammonia, and then lastly, convert from moles of ammonia to grams of ammonia. And our final answer comes out to 20.9 grams of ammonia. Let's look at another example. Oh, and like I said, as a reminder, standard temperature is 0 degrees Celsius or 273 Kelvin, and standard pressure is 1 atmosphere, 101 kilopascals or 760 millimeters mercury. So if we are not at both standard temperature and standard pressure, we're going to have to use the ideal gas law to get to moles of whatever our starting substance is before we can do our normal stoichiometry. So in this example, we're looking at the synthesis of water. We've got 2.25 liters of hydrogen reacting with sufficient oxygen at constant pressure and temperature of 98 kilopascals and 307 Kelvin. How many grams of water are produced? Again, we are neither at standard temperature nor standard pressure. So to get from volume of hydrogen to moles of hydrogen, we're going to have to use the ideal gas law. And then from there, we can continue about our normal stoichiometry. But the first step is figuring out moles of hydrogen using the ideal gas law. And using the ideal gas law, we end up with 0.0867 moles of hydrogen gas. Again, now that we've got our moles of hydrogen, now we can run this like a normal stoichiometry problem to get to grams of water. And our final answer comes out to 1.56 grams of water being produced. And that's how we can combine the ideal gas law and stoichiometry to figure out stoichiometric relationships when a gas isn't at standard temperature and pressure.